Hi there, welcome to the video tutorial for CompareSuit, a suite for analyzing large-scale multiparametric screens. This is the GitHub page of CompareSuit. From here, we can check out the latest release to download, or we can check out the wiki page of the suite. On the wiki page, we can find various information, including details about each module, how to download, install, use, and troubleshoot the suite. To download the latest release of the suite, we need to go to the release section of the GitHub page. Here, there are two zip files we can download, either we may download the data needed for this tutorial from the file repository page of the suite. The URL link to the data is given on the wiki page. Clicking on download, we'll be taken to the page listing all the sample files. Scrolling down to the bottom of the page, we can uncheck these two tables as practically we don't need them. Then click on zip and download. I have already downloaded the data. As you may see, the data is in FCS or fax file format. To know more about this file format, please refer to the wiki page. This suite needs an annotation file complying with a specific layout. You may find an example one in the downloaded data folder. Let's take a look inside. The annotation file provides the suite with enough information on the assay, such as how many plates there are, types of samples, and their locations. It must have specific number of columns and names detailed on the wiki page. If some of the columns are irrelevant to your assay, just leave them blank or populate them with something similar. Now let's check out the suite itself. As you may see, there are three subfolders in here named data, containing the assay data files, out, containing the readouts of the suite after each step, and SRC, which contains the source files. To run the suite in command line interface, aka CLI, we need to run these modules individually, stage 1 to 8. This tutorial is for the CLI, while the graphical user interface, aka GUI of the suite, is covered in another video. Let's start off by moving data files to the data folder of the suite. It is worth mentioning that a suite is a self-organizing tool, meaning that it has dedicated folders for input, output, and source files. Should you keep your input data or readouts in different locations, you can redirect the suite to them locations. Alright, now we're all set to begin the suite. Open the terminal or CMD window and redirect it to the source folder of the suite, i.e. SRC. Like this. Type in the following command to redirect it to SRC subfolder. Now let's move on to install the suite as instructed on the wiki page. The first step is to install the latest version of the bioconductor library. To do that, we need to start the R program first. Let's see if we already have the latest version of R installed on the machine. Another important thing is to make sure the rscript command is also available in the command line. Now we may fire up the R interpreter. As everything seems alright, we go ahead and install the bioconductor library. It should take a while if this is the first time you install bioconductor. It was a swift one for me because I already had it installed on my machine. Now the next step is to install the packages Comparsuit relies on. This is done by sourcing the install R script in the src folder as follows. We can take it from the wiki page and simply copy paste it in the command line. Depending on how many of these packages have been already installed on your machine, this installation process may take a while to finish. To test if the installation went well, we may again source the install script. We expect to see all the packages being loaded successfully. If there are messages complaining some packages don't exist, then you need to install those packages individually or reach out to your system administrator for assistance. Also, please refer to the troubleshoot section of the wiki page. Alright, everything looks fine. Now it is time to invoke the first module of the suit. Import is the first module of the suit. Its function is to discard broken files or those with too few events like cells or beads. All modules can be invoked by typing rscript and then the name of the module. This module can import tab delimited TSV, delimited CSV, or fact files. In case TSV and CSV text files are input, they are coerced to binary fax files for the sake of storage and programming. If we type such a command without arguments, we will see a full description of command line options, if any. The user shows this module takes 2 arguments. Now, let's set up this command for our run on this assay. Min events specifies the minimum number of events i.e. rows a file needs to be valid. Let's set it to 1000. I'm gonna copy paste it here. Use in URL to redirect the module to read in data files from a different location than the data folder. If we don't use this argument, then by default this module looks for data files in the data folder. I'm gonna set it to data folder. If we are on Windows machine, we need to use / instead. Then hit enter. The module is verbose enough and we may follow the output being printed. If there are invalid files given the input argument min events, then we will see such messages that a file has been moved to removed folder. What the module actually does is create a folder called remove and then move undesirable files to that. Let's let us later have a look at those files and delete them if we wish. Based on the size of the assay, it may take a while. but usually it is quite fast. Alright, we can see the list of warnings showing what files have been moved to remove given min events set to 1000. For example, this file has been moved with minimum events set to 1000. Now let's have a look inside remove. We will see here valid files and inside remove invalid files for the given input argument min events or those which were broken, not possible to read. If any file has been moved to remove, the annotation file is updated to include information on valid files only. If our input data files are text files, we can now delete them along with those in remove. The second module compensates for fluorescence spillover in fax files if the play reader was actually high-throughput fluorescence cytometer. If not, we can jump over this module and start the next one. In brief, this technology suffers from this phenomenon in which a fluorescence signal is detected by unassigned channels or detectors, and in the downstream analysis, it is necessary to compensate for this spillover. This module doesn't have specific arguments except for in URL for redirecting it to the input files. It will replace the spillover matrix in a fax file with the identity matrix and overwrites the file. Now let's take a look at the fax files after compensation. Here I have two files, one before and one after compensation. As you may notice, a new suffix compensated has been added to the end of the file name. For the file before compensation, we can see the compensation or spillover matrix. That's one. When compensation is applied by this module, this matrix is replaced with the identity matrix as in the second file after compensation, that the matrix is empty. Like this one, let me open the compensation matrix. Yes. Here you can see that the matrix is empty. The third module checks if the assay suffers from some sources of bias, such as edge effect, signal drift, autofluorescence, bioluminescence, and carryover effect in favor of specific regions of the plates. This module only corrects signal drift bias, as the other types should be experimentally avoided. Running the command with no argument placed prints the command line options. This module takes several arguments. The first one is the list of channels, as in the expression entry of the fax files or the columns variables in the CSV/TSV files. The next argument is correct. To reveal potential bias, we should set this argument to false, because initially we don't want to correct anything. Maybe correction is not necessary at all. Next argument, called direction, specifies the direction of bias. Basically, we need to assume a direction for the bias, either column-wise or row-wise. Practically, we should try both the directions, but one at a time. Let's set it to column-wise for now. The next argument specifies if the regression plots and play heat maps should be output. In case we want to redirect the input and output to other locations, we can use in URL and out URL. The default settings are data and out respectively. Finally, hit enter. Depending on the size of the assay, it may take a while, but usually quite fast. Alright, after a short time the output is ready in the out directory. There should be 3 files there with the suffix no correction, indicating that these plots show the original values of the plate wells. These files include plate heat maps, which show potential sources of bias in the plates, intraplate plots, which show signal drift within each plate, and finally interplate plots, which show batch effects between the plates. Let's start off with the plates heat map file. Each page contains the heat maps of all plates per channel, technically called marker, where each tile is colored by its median expression. For example, page 1 contains 3 heat maps for the 3 plates of the AML mass assay per WL6H channel, which measures CD11B expression, an important marker in immunology. As you may have already noticed, there is a distinguishable difference between the top left and bottom right corners of the plates. Here, orange-yellowish tiles represent lower values as opposed to those with green-bluish colors. The resultant or vector sum shows the direction of bias, top down, left to right, which is called column-wise in comparison. We can also see the same direction in the second plate. And in the third plate as well. In the second channel, we see a better situation, almost different colors spread across each plate. The predominant color on the left side of the plate is orange, while on the right side is yellowish. If I zoom in on the color palette or bar, we can see the border values. In the next channel, RL1H, measuring the granulocytic marker GR1, also demonstrate the same direction of bias as in CD11B. Finally, the last channel BL1H shows additional sources of bias, autofluorescence, and carryover effect. Let me close the affected columns off so we can see them better. Alright, the 8th column and partially the 9th column contain autofluorescent chemical compounds. This is why the affected wells have picked up the dark blue in the color bar. Except for the top part of the 9th column, this column as well as the 10th column don't contain such chemical compounds, but as we can see they have picked up high values, and probably that's because some of the autofluorescent compounds have been carried over into these wells as the pipette moved across the plate top down, left to right. This gradual change in color is clear across the plate. Unfortunately, since it is not possible to correct for this bias at this point, there is no other way but to remove worst affected wells and scrap these channels. Due to some technical issues during the wet lab experiment resulting in high variability and instability of the third plate, we also decided to entirely scrap this plate. It is worth mentioning that the randomization step in the experimental process in which chemical compounds are scattered over plates randomly is crucially important for being able to distinguish between bias and signal. Let's move on to check out the next file containing regression lines. As the name suggests, intraplate plot shows the general trend of values, i.e. median expressions, within a plate through a fitted regression line. These plots actually represent similar information as we saw in the plate heat maps. For example, this increasing trend in plate 1, channel VL6H, is because of the signal drift we already observed in its plate heat map. If you remember, since we set the direction of bias to column-wise, we are able here to see this drift in the signal by ordering the well values top-down, left to right across the x-axis. For example, the top left well of the plate corresponds to the first data point here, and the bottom right well corresponds to the last point. Time here refers to the order like by which wells are read according to the direction argument, top down, left to right. The y-axis, as said before, for the plate heat maps shows the median values of the wells. In other words, median marker expression of all cells in a well. MFI stands for median fluorescent intensity, although these values could be non-fluorescent. It's just a name. As we saw, the drift in the signal for channel VL5H was not that severe, so this is why the slope of this line here is kinda gentle. For RL1H channel, however, again the slope looks pretty steep because of the bias. Finally, the last channel, BL1H, looks sort of weird, and that's because of the autofluorescence and carryover effect we talked about. This abrupt cut here corresponds to the worst affected wells, and as I mentioned before, the wells of these columns are to be scrapped. We can also have a look at other plates. Alright, the last slide shows the interplate bias known as batch effect, if any. Firstly, we can also here see the increasing trends within plates. Quite prominent, huh? Wells of each plate are represented by a specific color. In addition to intraplate signal drift, we may notice that in general plate 2 has higher values than plate 1, and then both have higher values as opposed to plate 3. This is because of the batch effect introduced during the experimental process, probably due to unparalleled treatments. This is for the BL5H channel, then RL1H and BL1H, revealing autofluorescent compounds. Alright, now we have to move on to remove unwanted wells. We simply do this by modifying the annotation file. We just need to look up these undesirable wells and delete their entries from the table. There's no need for directly deleting data files. Okay, now that we know there is bias and also its direction, we may move on to correct for signal drift by setting correct to true. We set the direction argument to column, but in practice we should also check if there is bias row-wise, i.e. left to right, top down, and correct for it if so. Again, compare should only support these two orthodox directions. Since we have a scrap BL1H channel, I also need to amend the channel list. Also have it in mind that we eliminated several wells from the downstream analysis. That's it, let's run the command once again, this time for correcting the signal drift bias. After a short time, some new files are output in the out directory or in the location specified by the out URL argument. Corrections done, let's have a look at the plots after correction. First, we look at the data files. Alright, at this point, a new suffix should be added to the corrected files, and if you have run the compensating module, you would see an affix for compensation as well. In the out directory, as you see, several new files have been added. I start off by juxtaposing uncorrected plate heat maps with corrected ones. So this is WL6H before correction with the specified bias direction, and this is the condition after correction. As you may notice now, the regional bias is totally gone, revealing the true color of each well. Let me put them next to each other. For the BL5H channel, if you remember, the bias wasn't really that bad, and we can see here that even though the bias was little, it was still detected and removed. For the second plate, we see that even wells in the two corners, which are naturally the most affected ones by the signal drift bias, almost survive intact, and that's because the signal drift bias in this plate for this channel was trivial. For the last channel, interestingly, we see that unlike the uncorrected original plate 1, higher values are actually on the left side of the plate after correction. Next, we check out intraplate files. Here we can compare the trend of values before and after correction given a column-wise bias direction. One very important point here to make is that a good correction method should not distort the mutual proximity of data points after correction. Let's flip through the plot file to see if we can find something interesting to talk about. This is BL5H with trivial bias as the slope shows, and of course not much difference after correction. Finally, the last channel to talk about is RL5H, very similar to WL6H, and so on. Lastly, the interplate plots. So this is before correction and this is after correction. Remember, we removed plate 3 and so on. In addition to these files, there are some text files. These are actually the matrices used to generate plate heat maps and regression plots after correction. In case you don't like the output plots and want to customize yours, you can use these files for regression plots or heat maps, but have it in mind you need to assume a direction for bias. The force module checks if there is cell viability bias in favor of specific regions of the plates and corrects it if so. Similarly, running the command with no argument list prints the command line options. Like the signal drift correction module, to reveal this type of bias, initially we should set the correct argument to false. The argument lists remain pretty much the same, but with no channel list this time. Like before, we need to assume a direction for the bias, either column-wise or row-wise. Let's set it to column-wise. Finally, hit enter. We can wait on the output. It shouldn't take long. Alright, there we go. Let's have a look at the output. Oh, by the way, I just moved the signal drift stuff to a separate folder to keep output neat and tidy. Likewise, the output contains three types of plots. Getting started with the plate heat maps, we can see if there is a regional bias within and between the plates of the assay. Again, the difference between the two far corners of plate 1 is clear, indicating a column-wise top-down left-right bias. You could see the same bias direction for the second plate as well. Now let's go see what this bias looks like in the intraplate plots. Alright, we can see again an increasing trend across plate 1. In plate 2 also there is an increasing trend. This time the y-axis shows the number of live cells divided by 10,000 and the x-axis shows the order of wells according to the assumed direction of bias. Last file is the interplate plot. As you may have already noticed, one could say in general the wells on the second plate have higher values, i.e. number of live cells, as opposed to those of plate 1, indicating a batch effect between the plates. Okay, now let's correct this bias. We just need to set correct to true while the direction remains column. Press enter, and depending on the size of the assay, it may take a while. Alright, done. Let's take a look at the output after correction. First, I'm going to open the plate heat maps before and after correction so we can compare the plates next to each other. This is showing the situation before correction. As you can see here, after correction, this bias is gone, revealing the true color of each well. In the interplate files, we can see the situation before and after correction as well. What's it look like in the intraplate files? The increasing trend before correction is gone after correction in both places. Lastly, we look at the facts files. At this point, another corrected suffix should be added to the end of the file name. If we have had run the two previous modules, now we should see the suffix compensated, corrected, which means this file has been compensated, signal drift corrected, and viability corrected. This number here shows the original number of live cells initially stored in the file, not the corrected one. The corrected one is stored as a new keyword called viability, which is later used in the last module for clustering. The fifth module generates a similarity matrix. It uses an algorithm named compare, which measures similarity between two even samples within hypercubes using a dynamic programming approach. Invoke the module without arguments to see a full description of command line options. So like before, we use the same channel list. Let's just copy paste it from here. It also needs n, which is an integer by which each dimension is divided. Try something between 3 to 5 to get the most out of our assay. I'm going to set it to 5 for this assay. The next argument specifies the number of CPU cores. To run the module in parallel. Since I'm on a desktop machine, I must set it to 3, leaving at least one core free. But if you're on a computer server, you can use many more CPU cores, like I would say 20, 10, or even 30 or something for this size of assay. But always be careful with the available memory and consider that other folks may jump in to use the server. Let's hit enter. Depending on the size of the assay, number of CPU core used, and the amount of memory available to the module, this process may take a while. But the good news is that since the modules are independent, we can run all those modules up to the 5th one on our desktop and then continue on a computer server with many more cores and much more memory. I will show what it looks like when this module runs on a computer server. So let's wait a bit for the first will was processed. It means this will was compared to the rest of the assay in parallel. Alright, I demonstrate what it looks like when the 5th module run on a server with plenty more CPU cores and memory. First, I started screen terminal and initiate the module from there so it can still run after I log off. Let's run the command with more CPU cores like 60. Now we can evaluate the runtime speed here and contrast it with that of a desktop machine. Hit enter. Okay, it's already done for the first file, and second one, actually as time goes by, the processing time for a new file gets shorter and shorter. In other words, the module speeds up with time. Let's exit the screen and monitor system resources. As you can see, many more CPU cores, the green bars, are being used, but it is possible that new users join, causing the server to run out of memory and CPU resources. In this case, the operating system restarts a memory management process called paging or swapping, which substantially slows down the runtime. So it's not like that. We'd always be better off using more CPU cores. The bottom line is that the suit always has access to enough memory. For example, at the moment the memory is using 16 out of or 22 gigabytes out of 1.5 terabytes of memory. So we have a lot of memory available. Anyhow, for this assay, this module shouldn't take more than a couple of minutes to finish a process which should take naturally days or many hours. Let's return to the screen terminal to check the progress once again. As you can see, it has already processed many files. After a couple of minutes, the result should be ready as a similarity or affinity matrix. Let's take a look inside. It's a huge matrix with over hundreds of thousands of elements. Each value is the amount of a spatial similarity between a pair of samples. In general, the similarity between two samples can be measured from many aspects like across their dimension distributions or even common subclusters. Compare measures spatial similarity, meaning how much morphologically similar two things are in high-dimensional space. Talking more about the argument N of this module, consider two monozygotic twins. As we compare them across more features, they become less similar. This is what the n argument controls, the level of smoothing. Also consider three samples, A, B, and C. It is possible why B is more similar to A across a subset of features. It turns out that B is more similar to C across another subset of features. So by changing n, closely similar samples may change places. Regardless of its intermediate applications, similarity matrix is ultimately intended for clustering. The sixth module is an optional stage, and we may skip to the seventh one. This module generates a heat map of the similarity matrix, which comes in handy for finding impotent and potent samples very quickly, as well as it gives an overview of the assay. Let's run it. It may take a while because the matrix is huge. Alright, it's done. Let's have a look at it. The heat map is normalized between -1 and 1 so that the highest similarity is 1 and lowest one is -1, and then transformed by a power function to emphasize the extremes of the dynamic range. The size and color of each ball represent the amount of similarity, blue 1, red -1, and the focus of this heat map is on the highest and lowest values and their neighboring ones, not those between. The diagonal has been also eliminated. Using this map, hopefully we can find hits or impotent samples on the top left side with agility, as the map is sorted in ascending order of total similarity score. This part, top left. Since the clustering module infers the similarity cutoff from the similarities between negative controls, possible outliers in the set of negative controls should be removed beforehand. This is what the seventh module assists with. Also, be advised that if you have followed this tutorial using our assay data, there is no outliers among negative controls. Therefore, I'm using a made-up set just to convey the idea. Let's run the module, no arguments needed. In the out folder, we should find a heat map called control outliers. In the heat map, it appears that these two samples on the third plate are weakly similar to the rest of the ensemble, a property of an outlier. Such samples should be removed at this point. To do that, we simply delete their corresponding entries from the annotation file. We don't need to touch the similarity matrix or delete the facts files directly. Let's look them up in the annotation files and remove them. Since this is a dummy annotation file, the number of samples here are different from the main assay. At this point, you must have 465 samples in the main file. All right, the next one. Okay, in parentheses, if you have an enough number of negative controls, for example in this assay DMSO samples, well spread within and between plates. One or two outliers wouldn't really affect the inferred similarity threshold because their effect would be basically manifested in the third or fourth digit after the decimal point. A good practice is to remove them though, to be on the safe side. This is because in the clustering module, negative controls act like a magnet attracting impotent samples. So if there are some negative control outliers, they can falsely attract potent samples, creating false negatives. Okay, finally, the last module is clustering. Again, if we use the command without arguments, we can see command line options, if any. So like before, it takes the list of channels and the new argument here is NN, which stands for nearest neighbors, using UMAP function for generating the dispersion map of clusters. It is actually the size of local neighborhood in terms of number of neighboring sample points used for manifold approximation. Large values result in more global views of the manifold, while smaller values result in more local data being preserved. Recommended values should be in the range 2 to 100, since we don't know how many clusters the module will find. Let's set it to a big value so the module automatically will use all the clusters. Hit enter. The module is verbose enough and we can follow the printed messages like the similarity threshold inferred from the negative controls. Any two samples that are at least this amount similar in the similarity matrix, the one in the add folder, are placed within a cluster. Let me show you the sigmat again until it is running. Yes, that's matrix. So here is a list of clusters or clicks being found. All right, job's done. It found 135 clusters. Since the module uses a graphical clustering approach, clustering is tantamount to finding maximal clicks, which are locally the largest complete subgraphs. In out, you will find several readouts. Let's start off with the drug table. This one. Let me open it. All right. It is essentially the annotation table with more information added. The first column is the sample name in this assay, antineoplastic agents. The second column shows the concentration or dose of each drug. The third one, control column, simply indicates if the sample is a negative control, here DMSOs or not. One means negative control. So let me sort this column. Yes. So as you can see, all DMSOs are assigned 1. The next column, sim versus control column, shows the max value for which a sample is similar to any of control samples. By control samples, it means negative controls plus all those samples which were similar enough to them for the inferred similarity cutoff. As said before, negative controls act like a magnet, attracting impotent samples. For example, the strong similarity between this sample, vorinostat, a chemo drug, and a control one is 99.38%. For a sample which is not among the control samples, this value is less than the similarity cutoff for sure. First column holds the community numbers. A community is a connected subgraph that a clique is a subset of. In simple terms, a community is a neighborhood. The next column, fifth column, indicates how much on average a sample is similar to any other sample of the assay. For example, this one is 92.95% similar to any other samples. The next column, live cells, represent the corrected cell viability, if any, and the last column is simply the file name of the sample in the drug column. So now let's take a look at the sample graph. In this graph, nodes are samples and edges connect samples similar enough, given the inferred cutoff. The gray community consists of control samples, i.e. negative controls, and those samples similar enough to them. The gray community has number 0 in the drug table. You may see other communities as well, like community number 11, 6, 1, and many singletons. A maximal clique or cluster is a locally largest complete subgraph which can be a singleton or a subset of a community. The next graph is called dispersion graph. It is a maximum spanning tree. The idea is to build a tree connecting each sample or node to another sample with the highest similarity and keep doing this as far as possible. In other words, we cannot find another tree whose sum of edge weights is greater than that of a maximum spanning tree. The control sample together form the control node or root of the tree. Again, these are negative controls as well as impotent samples for this assay, impotent anti-neoplastic agents. Then you can see potent samples around the root with their dose written like this. In this assay, these are drugs showing a desirable response distinct enough from the DMSO in treating AML in a mouse model. As the tree branches and it spreads, more distinctive samples tend to lie farther from the root toward leaves. Now for example, this part, let me zoom in, or this part, the red color of edges implies lower similarities as opposed to the blue one. Also, edge weights represent similarity values. For example, this one is showing the similarity between these two samples is 99.6. In general, this graph can be potentially used to investigate different mechanism of action creating different branches. Let's look at some of the drugs here, for example. Here, different doses of the same drugs forming two branches, or another example, two different doses of the same drug are on the same branch, as you can see. And the one with the highest doses is actually the leaf. The next graph we look at is called dispersion map. The idea is to find supergroups, i.e. communities of responses, representing each click by its centroid, which is median. A U-map of clicks is constructed with respect to the control node, that is centroid of impotent agents. Here we can see, for example, around 5 supergroups or communities. Coloring or staining the dispersion map with medians across each marker could be visually informative for the investigator to agilely find out what makes supergroups different. The last page shows click numbers which correspond to those in the click table we will check out shortly. A similar plot called click heat map shows similar information as a heat map. Supergroups are ordered using a hierarchical clustering method which forms part of the phylum. Using this heat map is another way of finding out what makes supergroups different. Values are normalized between 0 and 1 per channel to make cross comparison possible. For each of the methods, one heat map has been generated. The next file is the click table, which shows click and community numbers for each sample. For instance, alectinib and nilotinib, with the specified doses have been found showing similar responses across the 3 markers used, so they have been placed in a cluster with ID 1 in community 1. The third column shows the corrected cell viability. Sorry, there is a problem with the 1000 separator in my Excel. And finally, the last column contains file names of samples in the clusters. For this assay, 134 clusters or clicks have been identified. Another piece of information we could get from the cluster table is that if there are experimental drugs or doses still in trials in our drug panel, which have been clustered with known drugs, we can predict their response and subsequently mechanism of action across the markers used before taking decisive steps. For example, according to the drug bank database, Navitoclax 1000 in row 64 has been used in trials studying the treatment of solid tumors. This drug has been clustered with imatinib 1000, which is a known drug for treating certain types of cancers. The other output is an RData object which contains all the information output by the 8th module. In case you want to create your custom plots, you can read this object in the R program. The last file is called centroids, which contains centroids of clusters. Each number is the median of channel values of all samples in a cluster. This is the dataset used for plotting dispersion clicks and clicks heatmap files.